Our next model comes from Bohr. And this is the closest to what we currently accept that is not the current model. This bridged a lot of gaps. Bohr worked in Rutherford's lab. He was able to solve atomic stability using two assumptions. First, he assumed that electrons are waves, as we saw from the de Broglie wavelength. Electrons are waves that are in closed orbits. Electrons being in closed orbits meant that they could only have a specific energy. We say that their energy is quantized. Quantized meaning it can only come in certain units. So electrons being in closed orbits, that would mean that we have our nucleus, and that is a plus. Let me see if I can draw this. So if we treat the electron as a wave, then that means that we can only have it be at distances where it completes a wavelength. So if you see, this is a continuous wavelength here for the electron to exist in. So like, let me come up with one. If it were to end with something like, if it were to end with something like that, where the wavelengths don't meet up with each other, or if we were to end with something like that, or it's not a full wavelength around it, that's not a viable orbit. An electron can't be there. It can't have that energy. So that's no. Another thing that he assumed is that angular momentum is also quantized. This means that it can only have specific values as well. We'll come more to that later. This model for the Bohr hydrogen atom is very good for, this model for the Bohr atom is very good for hydrogen. Skipping the math, which I will make available to you in case you get bored during quarantine, we're able to find the allowed radii of a hydrogen atom. The allowed radii becomes Rn, so n is the number of orbits out, is equal to n squared times AB, where n is equal to 1, 2, 3, and so on. So n is equal to any integer. And AB, the Bohr radius, is equal to a fantastic blob of constants. We have 4 pi epsilon naught over h bar, I'll show you what that means, h bar squared over m(e) squared. H bar is equal to h over 2 pi. We wind up dividing h by 2 pi a lot, so we just made a thing, we call it h bar. This is just a blob of constants. Comes out to be 5.29 times 10 to the minus 11 meters. So this is the constant that gives us the potential distances that an electron can orbit a hydrogen atom. Each orbit, or n value, has an associated energy. You can think you can think of it as we've got our nucleus, and then imagine these as waves. It's a lot harder to draw though. So each orbit has an associated energy. I'll call this N1, N2, and N equals 3. So we have N equals 1, N equals 2, and N equals 3. It's an N, not an M. When each of these orbits has its own energy level. So there's an energy that's associated with being in that orbit. As an electron jumps between orbits, so let's say that it's at a high orbit at like N equals 3, and it jumps down to N equals 1. So it goes from there to there. It's going to emit a photon that is equal in energy to the difference between these energy levels. The way that we find this is the energy that an orbital has. So the energy of the N equals 3 orbital is going to be equal to negative E1, the energy of the first orbital, and the energy of the first orbit, over N squared. Energy of the first orbit, which is in the derivation that I posted, so N equals 1 has an energy of 13.6 eV. So it's going to be negative 13.6 eV over N squared, where N equals 1, 2, 3, so on. So energy of the third would be equal to, so the energy of N equals 3 would be equal to negative 13.6 eV divided by 3 squared. So that's the energy that's inherent to the third level. We were also talking though about how it jumps. When it jumps, it gives off a specific wavelength. To find the emitted wavelength, we use 1 over lambda is equal to E1 over HC times 1 over m squared minus 1 over n squared. I'm actually going to change something in this. I wrote this out wrong. In this case, m is the final level and n is the initial. So m is where it ends and n is where it starts. So if it goes from 3 to 1, the initial, so if it goes from 3 to 1, then the final would be 1 and the initial is n. So n would be 3, m would be 1. That gives us the wavelength that hops off, that is emitted. Hydrogen has one of the most well-studied spectra. Some of the more prevalent energy transitions are classified by the end orbital positions. So if we have like the Lyman series, so this is a final, that's initial. So the Lyman series is any jump that ends at n equals 1. Any jump that ends at the first energy level. The Balmer series is any jump from a higher level down to 2. Paschen is from a higher level down to 3. And those all have characteristic wavelengths. Essentially, if we see these wavelengths given off, we know that there's hydrogen in whatever we're looking for. Bohr's second assumption that we talked about was of quantized angular momentum. Angular momentum it's very similar to the momentum that we were talking about, but in this case it's with a circle. So kind of like how torque is a rotational force, angular momentum is a rotational momentum. It's the momentum that something has while it's spinning. The way that we write so angular momentum is L, and we say that that is equal to what we call R cross P. In the more familiar notation, like we were using before, we would say that L is equal to R P sine theta. P is the momentum, so that P is equal to mv, and R is the radius. Since the electrons are at relatively fixed intervals, and they're now quantized, we know that the angular momentum has to be as well. Also, since we know that the direction of momentum is determined by the velocity, so if we have a plus there, got the electron is orbiting like that, the radius would be going in, and if it's moving like that, then the velocity will be going up. Meaning that theta will be 90. Since theta is 90, we can say that L is equal to R mv sine of 90, or L is equal to R mv.